Welcome to our factory. Today, I'll show you how tires are recycled into roads, step by step. Subscribe for more behind the scenes.
Every year, over 1 billion tires reach the end of their life, and they don't simply disappear.
Tires are engineered to survive heat, pressure, and time, which makes them almost impossible to break down naturally.
The same durability that keeps drivers safe turns discarded tires into a long-term environmental hazard.
When tires burn, they release toxic chemicals that contaminate air, soil, and groundwater for decades.
Tires trap water, creating breeding grounds for disease-carrying insects in urban and rural areas alike. Storing tires costs cities millions, space, monitoring, and constant risk management.
Landfilling isn't sustainable, so engineers had to rethink tires not as waste, but as raw material.
This is where the transformation begins, turning a problem into the foundation of modern roads. To recycle a tire, engineers must first understand what makes it so incredibly tough.
A single tire is not one material. It's a layered composite engineered for survival.
Tires combine natural rubber from trees with synthetic rubber made from petroleum.
Carbon black strengthens rubber, improves durability, and gives tires their deep black color.
Steel belts act like armor, allowing tires to flex without falling apart under load.
Sulfur bonds rubber molecules together, a process called vulcanization, locking flexibility and strength in place.
These chemical bonds resist heat, water, and microbes, so nature can't break tires down.
To recycle tires, engineers must first undo one of the strongest materials humans have ever created. Recycling begins long before the factory, starting wherever tires are removed from service. Millions of tires must be transported efficiently, or recycling becomes economically impossible. Facilities are designed to handle volume first, because scale determines whether recycling works.
Every tire is inspected because foreign materials can destroy expensive machinery. Tires are sorted by size and construction, since each requires different processing forces.
Metal rims and debris must be removed early to protect downstream shredders. Once sorted, tires enter controlled flow, turning chaos into an engineered process. Only after preparation can engineers safely begin breaking tires down. Tires can't be crushed. They must be torn apart using controlled, extreme force.
These blades are shaped to grip, shear, and pull, not slice, preventing rubber from slipping.
Shredders run slow but powerful, delivering massive torque without overheating the rubber. Instead of melting, rubber is mechanically forced past its breaking point. Heat is carefully managed. Too much friction would ruin the material. Regular maintenance keeps cuts clean and protects multi-million-dollar equipment. Shredding doesn't finish the job. It prepares the material for precision separation. Now broken down, the tire's hidden components can finally be extracted. After shredding, rubber is no longer alone. Steel and fibers are still tightly bound inside.
Magnets exploit steel's natural properties, pulling metal free without touching the rubber.
Once separated, steel becomes a recyclable product of its own.
Lighter textile fibers can't be removed magnetically, so engineers turn to airflow.
By tuning airspeed, fibers rise while rubber falls,
Pure physics at work.
Vibration and screening ensure only clean, uniform rubber moves forward.
Each stage is checked because contamination later would compromise the road.
Only after separation is rubber ready for refinement into a new construction material.
There are two ways to grind rubber: by freezing it solid or by forcing it apart while warm.
Cryogenic grinding uses extreme cold to change rubber's physical behavior.
When frozen, rubber becomes brittle, fracturing cleanly instead of stretching.
This produces smooth, consistent particles, ideal for high-performance asphalt.
Ambient grinding relies on force, not cold, to physically tear rubber apart.
Temperature is tightly controlled to prevent melting and material damage.
Each method produces different textures, chosen based on road performance needs.
Now refined, recycled rubber is ready to become part of modern infrastructure. To turn rubber into roads, engineers must carefully re-engineer asphalt itself. Recycled rubber is added not as filler, but as a performance modifier.
In the wet process, rubber swells inside hot asphalt, changing its chemistry.
Rubber absorbs oils, increasing elasticity and slowing crack formation.
The dry process treats rubber like engineered aggregate within the road. The result is quieter roads, better grip, and longer service life.
Every batch is tested because consistency determines road safety.
Once mixed, timing matters. The road is already waiting.
Before recycled asphalt reaches the road, it must survive years of stress in the lab.
These tests simulate the crushing weight of traffic, repeated millions of times.
Flex testing reveals whether rubber prevents cracking under constant movement.
Roads must endure scorching summers and freezing winters without failing.
Microscopic cracks predict long-term failure before damage becomes visible.
Rubberized asphalt also reduces vibration and road noise.
Only materials that pass strict standards are approved for public roads. This is the final checkpoint, where recycled material earns public trust.
Once approved, rubberized asphalt has a short window to reach the road. Timing is critical. Temperature and coordination determine final road quality.
The material must stay hot and uniform as it's laid down.
Machines shape the road, but human judgment keeps it precise. Compaction locks rubber and stone together for long-term durability.
As the road cools, its final properties are set.
Drivers may never notice, but the difference lasts for decades.
What was once waste now supports millions of journeys every day.